In this video, we're going to review the concepts of domain and range. We'll talk about what those terms mean, and we'll also do several examples of how you go about stating the domain and the range for a function or a relation that is not a function. So what do we mean when we say domain and range? Well, those two terms actually just refer to lists. Specifically, when we say domain, we're talking about a list of input values. Okay, so the set of the inputs in a relation is what we call the domain. Now, usually, or I shouldn't say usually, but very often in mathematics, the inputs in a relation or the inputs in a function are the x values. So when we say domain, we're usually talking about the possible x values for that relation or that function. Similarly, range refers to the list of outputs in a relation, or the set of outputs. Now that's often called the y values in mathematics. So when we talk about domain, we're talking about a set or a list of all the inputs or x values, and range is the output values or often the y values for a relation. So let's do some examples to see how we go about stating the domain and range. And sometimes it's pretty easy. So for example, take this one. This relation here consists of several points. We have 5 points. And we are going to state the domain and the range. Now remember, the domain is simply the set or a list of the x values that we have. And we only have 5 of them here. We have -2, -3, -4, -3, and -1. Those are our x values, and sometimes we call them the input values. So pretty easy to list those numbers, right? I mean, there's only 5 of them. Actually, we don't even have to list 5 of them because -3 is repeated here. So we really only have to list 4 numbers, and that's very easy to do. So that's exactly what we will do in this case. We'll just list them. Now, very much like the way that our relation was kind of written here, it's a list of points. We use squiggly brackets or these braces to show that we have a list of things. That's what we have to do when we list our x values or when we write our domain. We have to state that list inside those squiggly brackets. That's a way of notating that we have a set of something in mathematics. So there it is. The domain is -4, -3, -2, and -1. Notice that even though we had 2 x values of -3, we only needed to list it one time here in the domain. There's no need to repeat that. Similarly, the range is the set or the list of all the y values, and we have 2, 3, 4, 5, and 6. So 5 different y values there. Very easy to list 5 numbers, right? So let's just do that. We'll get our squiggly brackets, and in there we'll write our list. I have them in order here. That's not actually necessary, I guess, but it's kind of a courteous thing to do. So 2, 3, 4, 5, and 6 is our range. And while we're at it, let's just remind ourselves what a function is. Is this relation a function? Well, we just need to look to see if there are any x values that have more than one corresponding y value. And aha, we do. We have -3 corresponds to a y value of 3, but -3 also goes with a y value of 5. So this is not a function. Okay, let's move on and try some other examples. And I'll keep putting this reminder up. Remember, the domain is really just all of the x values that we're dealing with, and the range is just all of the y values. So when we see something like this, oh, sorry, that a little quick there. This is all we really need to do is take a look at the x values and take a look at the y values and state them, and that will give us our domain and our range. So what is the domain? It's just a list of all the x values. Now we only, once again, have 5 of them, -2, -1, 0, 1, and 2. Those are our only x values, so let's just list them. Just don't forget the little squiggly brackets. So the domain is -2, -1, 0, 1, 2. Same thing for the range, really. We only have 5 values here, so it's so easy to list 5 values, so we'll just list them. The range is -10, -3, -2, -1, and 6. Is this relation a function? Do we have any x values that correspond to more than one y value? We do not. Okay, in fact, we don't have any repeated x values, so that's definitely not going to be something that occurs. So this is a function. All right, on to the next example. Let's take a look at a graphic example here. For this one here, we have a graph. Now it does just consist of a bunch of points, but it should be easy enough to list the domain and the range just like we did in the previous one. So the domain is all of the x values we have. So what do we have? Well, take a look at our point. We have an x value of 1 here. We have an x value of 2 here, 3 here, 4, 5, and 6. Those are all of the x values, so we'll just list them. There we go. Our domain is 1, 2, 3, 4, 5, 6. What's our range? Well, for our 6 points here, we just want to look at the y values. So this one looks like it corresponds to a y value of 1. This point here has a y coordinate of 3. This one's got a y coordinate of 6. 10 for this one. What was that? 15 for that one. And 21 for this one here. So we'll just list those numbers as our range. No problem. 1, 3, 6, 10, 15, 21. Is this relation a function? Absolutely. Any point here, any x value has only one point with it, which means every single x value that we have has one corresponding y value for that particular x value. So it is a function. All right, let's move on to something slightly more complex. Notice here that we have a graph that is no longer just a bunch of points. It's actually a continuous graph, in this case a straight line. And I'll just give you a heads up, when I use these graphs, if it extends all the way to the edge of the grid like this, it's implied that that actually continues on infinitely far in that direction, both up to the right and down to the left in this case. So what's going to happen when we try to state the domain and the range for this? Well, in the previous examples, we could just list the values. It was really easy to do. But if we think about this, we have a problem. There are a lot of x values that we're using here. So for example, are we using an x value of 1 in this particular relation? We are. The point is right there. We're also using an x value of 2. The corresponding point is right there. But in between 1 and 2, there are infinitely many values for which we have a piece of graph up here, right? So we have infinitely many points. That's going to be really hard to list. So what x values does this graph cover? Well, remember, it continues infinitely far in this direction and in this direction. Are there any x values that we miss, that we don't cover? No, there's no breaks, or there's no holes. There's no value of x that I could choose on the x-axis and not go and find a corresponding piece of graph for. Any x value has a piece of graph that has that x value for a point on it. So how are we going to do this? Well, it covers all of the x values. How do we state, or how do we list all of the x values? Well, we need a clever way of doing this. And what we do is we really want to state that the x values include every real number. We're talking about real numbers here. And in this particular course, the only types of numbers we'll be talking about are real numbers. They're all the numbers you've dealt with before. And the way we write that is like this, okay? So again, we are talking about a list of numbers. So we need these squiggly brackets or these braces here. We're talking about our domain. So we're talking about x values. And we want to say that x is every real number that we have, every real number possible. So the r is what represents real numbers. Now it's kind of a fancy looking r there. We do that in math. This symbol here is, well, formally that means is an element of. So x is an element of the real numbers. That's how we actually state this notation here. What it means is essentially x can be any real number. Okay, and that's true. So for the domain, any real number for x is what we have, and that's how we state it. Okay. Now, let's talk about the range. Notice that this graph covers all of the y values too, right? For any y value, there is a corresponding piece of graph. So there's a corresponding point that has that y value. There are no breaks or no gaps in this graph. It continues upward to the right and downward to the left forever. So we actually do have graph or we have points for every single y value possible. So we need a way to state that. Way too many values to list. So again, we use this fancy notation. The only difference is this time, because we're talking about the range, we're talking about y values. And we want to say y is the entire set of real numbers. Y can be any real number. So y is an element of the real numbers. Don't forget the squiggly brackets because we are talking about a set of numbers. It's just a very large set here. All right. And while we're at it, is this a function? Sure is. It passes the vertical line test. No matter what x value you choose, if you draw a line there, it hits the graph in only one spot, which means every x value has only one corresponding y value. So it is indeed a function. All right, let's just do a few more examples and we'll wrap things up here. How about this parabola? Let's talk about its domain and range. Okay, well, for the domain, it does cover all of the x values. Again, remember, because this goes right to the edge of the grid here, it does continue indefinitely in that direction and in that direction there. So it's going to keep going to the right forever. It's going to keep going to the left forever, which means any x value that I choose will have a corresponding point on this graph, which means that this graph kind of covers all of those x values. So we've already seen this. We just say that the domain is the set, the entire set of real numbers, and that's the way we write it. Now, does that happen for the range? Not quite, because this graph has a minimum point here at 0, and then from there it goes upwards. So you never get graph down here in the negative. So when it comes to y values, the lowest possible y value that we'd have for a point on the graph here, it happens right here, and that's a y value of 0. All of the other y values that we're dealing with for this particular function, this particular relation, are greater than 0. They're higher than 0. Okay, we're talking about these y values here. So we need a way to state we're talking about a lot of y values, okay, and they're all real numbers, but we're only talking about the y values that are 0 or higher. And here's how we would go and write that. Keep in mind, it's still too many to list. You can't actually list them, so we have to use our fancy notation. So take a look at this. Squiggly brackets, because we are talking about a set of numbers. Y is an element of the real numbers. So that really just says we're talking about y values that are real numbers. Okay, and we have a lot of them. But this line actually means such that we only want y values that are greater than or equal to 0. Okay, so we're talking about infinitely many real numbers for our y values, for our range, but we're only talking about y values that are greater than or equal to 0. And I'll read this for you formally. This is y is an element of the real numbers such that y is greater than or equal to 0. We're talking about all the y values that are 0 or higher. That's how we state the range here. Okay, let's try this one here. I'll do it fairly quickly because it's now becoming, it's going to be a lot of the same type of thing. Let's talk about our domain. What x values do we have in this particular graph? What x values are we dealing with? Well, the lowest one is -2. The highest is 2. But notice that we have this nice continuous graph both on the bottom and on the top from that -2 x value to the +2, which means that for any x value between -2 and 2, we have a point on the graph that has that x value. Actually, for most of them, we have 2 points, right? One above and one below. Still way too many to list, though. So we use our fancy notation. We say, what we want to say is the graph covers all of the x values between -2 and 2, including those values. And here's how we write it. Oh, sorry, by the way, the y values do the same thing. The lowest is -2, the highest is 2, and we have points that have y values everywhere between -2 and 2, right? This nice continuous graph here, and on the other side as well, has a bunch of points, and for those points, we cover all of the y values between -2 and 2, without any exceptions. There's no breaks or gaps or anything. So how do we state it? Like this for the domain. X is an element of the real numbers, so we're talking about real numbers, a lot of them. We're talking about x values such that our x values are between -2 and 2. And I'm going to trust that you're comfortable with this inequality notation here. Essentially, you're saying that our x values, if you read it from the x to the right, they have to be x values less than or equal to 2, but also, read it kind of backwards here, x values that are greater than or equal to -2. The other way you could say that is -2 is less than or equal to the x values. Essentially, you're saying we want x values that are less than 2, greater than -2, including those two values. That is the set of all those x values between -2 and 2. That's the way we write it. And the same thing happens for the range. So you have all of the y values between -2 and 2. Okay, one more example here, and then we are finished with this review. Because in this graph, I've kind of stopped the graph and put two solid points here. This graph does actually stop there, and it includes the points at the end there. So very quickly, we have a nice continuous curve here, so we're not seeing any gaps or breaks in it. So what is our domain? Well, it would be all of the x values that we cover from the left side of this to the right side of this. And the left side is corresponding to an x value of -2. Right side corresponds to an x value of 4. And we want all of the x values between -2 and 4. So our domain is going to be everything from -2 to 4. And our range, well, the lowest y value we have actually occurs right here. That's a y value of -1. And the highest y value is up here, which looks like it's at 15. And because we have this nice, smooth, continuous graph, we have points that correspond to every single y value from -1 up to 15. I can always, for any of these y values, I can find a point on the graph that has that y value, which means our range is everything from -1 to 15, including those values. And as we've seen, this is how we write that. So for domain, x is an element of the real numbers such that x is between -2 and 4. So from -2 to 4. And our range is a set of all y values. So y is an element of the real numbers such that y values, we want the y values that fall between -1 and 15. Okay, so -1 all the way up to 15. Every single y value between -1 and 15, including -1 and 15. And that is the range for this function. And that is it. So at the end of the day, remember, domain is just all of the x values we're working with. Range is all of the possible y values, or sometimes we call it the output values. And when we state the domain and range, we're just going to list those things, all of the x values for our relation and all of the y values for our relation. It's just that sometimes it's actually really tough to physically list those things. So we use our fancy notation where we say that we're talking about real numbers with some type of condition or restriction on those that set of real numbers. So there you go, domain and range. I hope that helps. Take care.